them both into one video. Okay, so I started recording again. Hopefully that worked. Okay. So you're going to use your ice table. So first the expression HNO2. When do you know when to use an ice table? If you're given a Ka. If you're given a Ka, it's signaled that it's a weak acid. So it's not going to completely dissociate. Whereas for strong acids, you're not going to be given a Ka because the Ka is going to be too big, or not too big, don't worry about it. If it's a strong acid, you won't be given a Ka. It should say that it's a strong acid, or it should be, I don't know if you guys are required to memorize strong acids versus strong bases, you'll know. HNO3 is a strong acid, HNO2 is not. So if anything that, it's not. So if you remember your strong acids, you know it's not a strong acid. Also, you know it's a weak acid. If it's not strong, it's weak. So there's only like a limited amount of strong acid. Everything else is weak. And it also gives you the K. So that's like signal that it's not going to like dissociate completely. So plus water gives you NO2 minus aqueous plus H3O plus. That's also aqueous. So now ice. So you have, oh, yikes. It's the reverse. Because it gives you the concentration of the acid. Okay, so that's a little different. Let me just erase this. No, water stays the same. So NO2 minus and HNO2 and OH minus. This is a little different. So 0.25 goes here. It's going to be minus X, 0.25 minus X. That doesn't matter. It's going to be 0, 0 plus X and X and X. Okay. So before you can start to solve, you have to recognize the fact that you're giving Ka, but you need Kb. Because this reaction is the expression that you're going to get from this, OH minus HNO2 minus, no, not minus, sorry, over NO2 minus is going to be 4 Kb. So your Kb, you got to find out what that is. It's 10 to the negative 14 divided by 4 times 10 to the negative 4. And this is the same thing as you do with your H3O plus and OH minus concentrations. It's the same exact thing. If you multiply Ka times Kb, it's going to get times 10 to the negative 4. Or negative 14. It keeps negative. So 10 negative 14 divided by 4e negative 4. So your Kb is going to be 2.5 times 10 to the negative 11. So now you can solve. And now you have everything you need to solve. So we got 2.5 times 10 to the negative 11 equals x squared over 0.25. You can ignore the x because your times 10 to the negative 11 is really small. The Kb is really small, so you can just ignore it. And it will save you a lot of time. So times 0.25, multiplied by 0.25 on both sides. So you get 6.25 times 10 to the negative 12 equals x squared. We'll take the square root both sides. And your x is going to be 2 times 10 to the negative 6. Now this gives you your OH concentration. So your OH minus concentration equals 2.5 times 10 to the negative 6. So if you want your H3O plus concentration, you have to take this and divide 10 times 10 to the negative 14 by this number. To get 4 times 10 to the negative 9. And then your pH is going to be, like it said, 8.4 or 8.39 or 8.397, same thing. Okay, so which of the following 0.01 molar solutions will have the highest pH? Is going to have the highest pH. Okay. So you know it's going to have the highest pH if it has the lower Ka. So Ka or if it has a low Ka, it's not going to dissociate as much. Whereas something that dissociates a lot is going to have a lower Ka or lower pH, yes. Because remember, lower pH means it's a stronger acid. If it has a stronger Ka value, it's going to, what am I trying to say? Is going to not associate as much. Also, the reason why it's Na2CO3, Na2CO3 is basic. It is basic. So you already know it's not going to be any of the acids. Not going to be the acids. And also, if you know your K, you can also solve for your, so if you know the Ka of H2CO3, you know the Kb of HCO3 minus. That's just times 10 to the negative 14. So you divide that by 4.3 times 10 to the negative 7. That will give you your Kb of HCO3 minus. And if you do the same thing here, this is the Ka for HCO3 minus. So you can use this to get your Kb for CO3 2 minus. And this one, because the Ka is the smallest here, your Kb will be the largest. And if you have a larger Kb, that means it's going to be more basic. I hope that makes sense as to why it's not E. That makes sense. Not E, C. C. Right answer. Okay. So which of the following reactions will have the largest KEQ as temperature increases? Which will have the largest KEQ as temperature increases? Okay, so this reaction here, these three reactions are exothermic. So that means you can treat them all as if it has plus heat. Plus heat. So if you increase temperature, it's going to shift towards the reactants. That means your K or your not your or yeah your KEQ is going to go down. So it's going to decrease. Whereas for this one, for these two, Heat is a reactant. And you also want to pay attention to which one is the most endothermic. So B is the most endothermic, so it's going to have the greatest impact when you add heat. That makes sense. I think the formula is natural log K2 over K1 equals negative change. It's either activation energy, it changes, but it's similar. 1 over T2 over T1. If you were to like manipulate the equation, you could also see that. I'm pretty sure you're going to get that equation or this equation. Okay. So determine the equilibrium expression for the following reaction. So you're only going to focus on aqueous and gaseous states. You don't focus on solid and you don't focus on liquid. You can have both aqueous and gaseous in the same thing. It just has to either be aqueous or gaseous. So it doesn't have to only be aqueous, it doesn't have to only be gaseous. It can be both. Or not where one thing can be both, but you can have both, you can have gaseous and just as long as it's not a solid or a liquid, it can work. Okay. So addition of a catalyst to an equilibrium system increases the KEQ. So important thing to note that catalysts never change the thermodynamics. It doesn't have any effect on equilibrium. It won't change it at all. So A is wrong. Shifts the reaction to left, again, does not have any effect on equilibrium. Again, no effect on equilibrium. Increases the ratio of products to reactants. This is again thermodynamics. That is essentially your KEQ, the ratio of products to reactants at equilibrium. So no, it does not affect the thermodynamics of the reaction at all. Doesn't affect it. So E is the correct answer. It does not have an effect on equilibrium. Adding a catalyst does not change equilibrium, because even though it might change the rate of the forward reaction, it at the same time changes the rate of the reverse reaction proportionally. So it's not going to change equilibrium. Okay, so gases W and X react in a closed vessel to produce Y and Z gases. The reaction initially has 1.6 atm of W gas and 1.6 atm of X. The reaction is allowed to reach equilibrium. If the Kp value of the reaction is 0.4, what is the equilibrium pressure for Z gas? Okay. So we got ICE, so luckily it's 1.6 and 1.6, so these start off as 0 minus x plus x plus x. So 1.6 minus x, 1.6 minus x, x, and x. So, 0.4 is going to be equal to x squared over 1.6 minus x squared. So you take the square root of both sides. And hopefully I answered your question from before about why it doesn't have catalyst or what does have what does have an effect on changing pressure, changing temperature. Well, no, actually, temperature is the only thing that changes equilibrium itself. Well, no. Changing the concentration, changing the pressure, changing the temperature, changing volume, all affect equilibrium, or they all have an effect on shifting equilibrium. Temperature, however, is the only one that can change your KEQ value. But all of those other things have effect on equilibrium, not catalyst. A catalyst doesn't change anything. It other than the kinetic of the reaction. So increases the rate, but because it increases both the forward reaction rate and the reverse reaction rate proportionally, it's the same. So it doesn't have effect. Sorry, I didn't answer your question. I thought I read does not have an effect. I was like, oh, it's a catalyst. Okay. Okay. So square root 0.4. So 0.63 equals x over 1.6 minus x. That will go to 1.01 minus 0.63. Sorry, x equals x. So 1.01 divided by 1.63. So x equals 0.62. And this is just me like quickly like working. All I did was just solve for x. So if you were to have gone through and add 0.63 on both sides and then divide, you would get 1.63x equals 1.01, and then you just divide by 1.63 to get 0.62. Okay, so we try to remove that. Yikes, I didn't like that. Oh, still on a picture. Okay, so I'll move this down so it's easier to see. So HNO2 has a Ka value of 4.5 times 10 to the negative 4. Which of the following shows the correct ranking of highest concentration and lowest concentration of species in a 1.03 aqueous HNO2 solution? Okay. So you can work this one if you don't understand it conceptually. You just need your eyes. So this is 1 ice minus x. This doesn't matter. So 1 minus x, 0, 0, plus x, x, and x. Okay, so you got x squared over 1 minus x equals 4.5 times 10 to the negative 4. Okay, so this is going to require a quadratic equation. Or if you did not want to do that, what you could do is recognize the fact that your Ka value is small. It's not super small, but it's still pretty small. It's small in relation to the concentration of HNO2. So even though it's not like 10 times 10 to the negative 4 times smaller, it's still small. Like a K value that is 1. So pretty much at equilibrium, any equilibrium constant lower than 1 means that you're going to have more reactant at equilibrium than product. A K value that's greater than 1 is going to be more product than reactant at equilibrium. That makes sense. Because if you think about the expression of K is it would be your NO2 H3O plus. So you have more product or more reactant then you do product since your Ka value is 4.5 times 10 to the negative 4, because it's lower than 1. So if your Ka value is lower than 1, that means you're going to have more products than you would have, more reactant than you would have product. It's not going to dissociate completely, if that helps, like, you understand. Whereas something like a strong acid would definitely have more product than reactant. But in this case, if your K value is lower than 1, that means your equilibrium favors reactants. Greater than 1, it favors products. So you can look at this conceptually. So you know that your reactant is going to be greater. So HNO2 is going to be greater. That's going to be greater than H3O plus. So anything and NO2 minus. So anything that has that, you can cross it out. So cross out that, cross out that. Okay. And then you know HNO2 is an acid. So if you're going to make it, you're forming H3O plus in your reaction. So that means it's going to be acidic. So if it's acidic, that means you're going to have more H3O plus than OH minus, which B and A both have. But also remember that your H3O plus concentration is going to be equal to your NO2 minus concentration. So it couldn't be B. Because if you know your OH minus concentration is smaller than H3O plus, your NO2 minus concentration can't be smaller than OH minus. NO2 is going to be equal to H3O plus because they're both X. So it's going to be A. Because you have more, your reaction it has a Ka that is less than 1. So it's going to favor reactants. You're going to have more reactant than product. And it's an acidic solution, so you're going to have more H3O plus. It's setting up which equation? HNO. Confusion where does the confusion lie? Is the thing to understand. Like,
okay, I'm opening up my mic because it's too much to type.
Yeah.
Basically, figuring out how you know what's being reacted to. Like the HNO2 to H2O. Like how to just write that out. They don't give it to you.
H3O plus or OH minus, like knowing that.
Like the entire thing. Actually, no, the product side. Yeah.
Knowing the products?
Yeah.
Yeah. So Rima said, is it because H2O adds to every reaction? Yeah. So these reactions are always going to happen in water. The key here, it says aqueous. Anytime it says aqueous is water, like, aqua, so water. So these reactions are gonna happen in water. It tells you, well, HNO2 is an acid, so it gives you your Ka value. It gives you your Ka value. So this is a reaction that's gonna form. I mean, maybe if they gave you a Kb value, but it's acidic if your Ka value is bigger than your Kb value. And in this case, it most definitely would be. But I think that if your trouble is figuring out do you know which one is the acid? Like can you tell it's an acid? So you don't know which one is acid. Yeah, your Ka value is acidic because your Ka value is greater than your Kb value. So think about the relationship between Kw is Ka times Kb. So if you were to find your KB, your KB would be, so KW is always going to be 10 to the negative 14. So it's going to be 4.5 times 10 to the negative 4 equals your KB. So it's going to be so your KB is going to be equal to 2.22 times 10 to the negative 11. So it's smaller. So if it's smaller, that means this is acidic. Or actually better, think of better things. Don't solve for your KB. Remember the Ka of water. The Ka of water is times 1 times 10 to the negative 7. So whichever one in the reaction has the greater Ka is the acid. If you remember that. Ignore all that. Ignore all this. Ignore it. You can do that, but please ignore it, because this will save you a lot more time. Does that make sense? So the Ka of water is 1 times 10 to the negative 7. So the this greater Ka is going to be the acid in the reaction. That's how it goes. Yeah, you can do that, because Ka is ultimately what determines the strength of the acid. So a stronger acid is going to a stronger acid is going to want to dissociate more. So the more favorable reaction is going to be HNO2. Oh, sorry, that's eraser. HNO2 going to NO2 minus H3O plus is going to want to dissociate more because it's a stronger acid. So compare Ka values. Greater Ka value means it's the acid, and water is times 10 to negative 7. Hope that's a better explanation. That helped. Yeah, you should be given one of their K, because you couldn't guess unless it told you it was an acid or it was the acid. But I mean, in all of these reactions, you kind of need your Ka value unless they give you your equilibrium concentrations. And if they give you your equilibrium concentration of one of the, they're gonna give you a product, or they might not. But I wouldn't bet on it. I hope that helps. Let's not think about crazy hypotheticals. So 0.1 molar solution of weak acid HX is 3.5% ionized. What is the Ka? Okay. Mm-hmm. So you remember your percent ionization formula. I'm just going to do H3O plus because that will save confusion. Over, and it's the initial acid concentration. So the initial concentration, and this is times 100%. So you're given the initial concentration of HX. So, and you know the percent ionization. So you got 3.5% equals, let's call the H3O plus concentration X over 0.1 times 100%. So you can divide both sides by 100%. So you're going to get 0.035 equals X over 0.1. Which is just, So that's your H3O plus concentration. So you know your equilibrium concentration for H3O plus. And I think the reason why I made this X was because you got HX plus water. It's going to give you X minus plus H3O plus. So ICE, this is 0.1. So minus X is going to be 0.1 minus X. This doesn't count. 0, 0 plus X, X, and X. So this X here is going to be this same X here. Because this is what it's saying. This is the H3O plus that formed when you put 0.1, or that's H3O plus that formed from 0.1 m of HX being in water. So this X value, this is your equilibrium concentration, because you use your equilibrium concentration of H3O plus in your percent ionization. So if you know that this equals 0.0035, that means this also equals 0.0035, and you know that it's the same X that's here too. So your equilibrium concentration of HX is going to be 0.1 minus 0.0035. So that's going to be 0.0965. So you can do your KEQ now. You have all of your equilibrium concentration, X minus times H3O plus over HX. And that will equal that's going to equal 1.27 times 10 to the negative 4, which it does. That's great, because I forgot to look at the answers. Consider the equilibrium reaction below. Which of the following will increase the concentration of the CO3? Adding a catalyst. Remember, no, it never affects the equilibrium reaction. It doesn't. Adding acid. The acid in this case is HCO3. That's your acid. Adding acid will not increase the concentration. I'm not entirely sure. Oh, sorry. No. It is water. This is like flipping your this is like flipping your see how H mixing CO2 or CO3 minus and H2O produces OH minus. So that means this is a base. This one is tricky to explain. Well, not entirely sure I have a good explanation for this one. So you know your water will not affect really. not entirely sure for this one. Ultimately, I think it might be the fact that your stronger acid is water. I think it's because water is stronger acid than, I think water is a stronger acid than HCO3 minus. So adding acid would increase, adding acid would, I think it would cause it to react with this CO3 2 minus and shift equilibrium actually this way, if that makes sense. I'm pretty sure it doesn't. Like, I'm almost positive it doesn't. But if you add acid, it should. Yeah, because this is base. This is your acid here. This is conjugate acid. This is like this is OH minus. So this is like if you like flip it, it's like a basic reaction. So adding acid is gonna react with this base here. Yeah, this base here is stronger than OH minus. So it's going to react more readily when you add acid. So it's actually going to decrease this concentration. I'm not entirely sure how you'd be expected to know this. Based on what guys have learned, this is like one of those, this is a tricky question. But yeah, decreasing the temperature is exothermic, so you can treat it like heat is here. Decreasing temperature shifts equilibrium over here. And increasing pressure, remember, you don't focus on water. So the side that has So increasing pressure is going to, for gas. So this is gas. So be like cognizant of that. The fact that this is not so pressure is not really gonna affect this. Changing pressure only affects gases. It's not gonna affect them. Yeah. That helps. I hope it does. Adding acid, yeah. This is a stronger base than OH minus. I think that's the explanation I should have gone with. This is a stronger base than OH minus. You can tell because OH, that's actually not true. Ultimately, I guess it's like if you rewrite it, if it was written differently, I swear I'd have a greater time at explaining this, like this. But then it would change this, which doesn't really matter too much. So this here's your base is going to react with whatever acid you add, if that makes sense. It's going to react with that. So it's going to get consumed. So pretty much adding acid means decreasing this base's concentration. Yeah, that. Okay, we'll move on. So what is the H3O plus concentration in a solution that has a pOH of 3.3? So this one is not bad. So 14 or pH equals 14 minus pOH. And 10 to the negative pH equals your H3O plus concentration. So pH gonna equal 10.7. So, and then your H3O plus concentration is gonna equal, and that was just like quick math I did. If you wanna do it out, you can. So it's going to be 1.99 times 10 to the negative 11, which is pretty much 2. Oh, that changed stuff. Which is pretty much just 2 times 10 to the negative 11. Yeah. So it's that answer. You would just round in that case because it in this case technically you would have to round because it's 1.995. You round up the 9, round up the other 9, get 2. What is the KP for the following reaction given the information in the table? Okay. So this is this is a fun one. So this reaction here, pretty much what you want to do is get this reaction. You want this reaction. So this is kind of like your Hess's law kind of stuff. All this stuff. So looking at this, you have everything here that where you want it to be. So first looking at either your product or your reactant, like or let's just start with the product or reactants. Say like N2 is right place, O2 is also in the right place. Now what's wrong with that is the fact that their concentrations are 2 times less than they're supposed to be. So let me fix that. So now I have N2 plus 2O2 gives me NO2. And when I do that, I have to square my equilibrium constant because I doubled everything. And remember, in your equilibrium expression, coefficients become powers. So if you multiply everything by 2, you take your equilibrium constant. Okay, and then you don't want NO2 because NO2 is not your product here. N2O4 is. So N2O4 is right here. It's reactant, so you don't want it to be reactant. You want it to be a product. And it also has the wrong coefficient. So you want it to be that I mean not second power. I didn't multiply that by 2. The NO2 concentration. I was like, that's not gonna. So it's 2 NO2. Okay, that changes everything. So you multiply this equation here by 2 and flip it. So you get 2 NO2 and 2O4. So whatever you do to the equation, you got to do to your equilibrium constant. So you flipped it. So it's 1 over x. And then it's multiplied by 2, so you square it. And then when you combine reactions, because you're going to eventually combine this, so this is going to cancel, this is going to cancel. So now your final N2 plus 2O2 gives you N2O4. You combine reactions, you multiply equilibrium constant. So you're squared. This was kind of one of those like puzzle questions. You just kind of have to do different things, manipulate different things, you're pulling all kinds of different information in order to solve this one problem. So it's like really testing what you know. So which of the concentration of HF has the greatest percent ionization? Okay, so you're going to, for this one, it's going to have the greatest percent ionization if it's going to, whichever one has the smallest concentration. And the reason why is because pretty much you could also rewrite your percent ionization as this. So it's going to be your H3O plus concentration over the concentration of your HF minus H3O plus times 100%. So you're going to want the smallest denominator. Technically, regardless of the concentration that you start with, your H3O plus concentration is not really going to be different. Thanks. Like it's not going to change. Like if you think about the nature of your ice table, the concentration that you have that you initially have of acid doesn't really ever affect how much H3O plus. Never does it. Has no effect on it. So you can add as much acid as you want. That thing's only going to dissociate so much. Based on dissociation is dependent on your Ka value. So because this isn't going to change in this case, this is going to be a constant. It's not going to change. This is just I didn't this isn't a formula that I don't think you were given this formula. I'm just talking about oh, my bad. Sorry. Actually, it's not that. It should be, sorry. Because it's your initial concentration of acid, not the change. So because, yeah, you're still, the same thing applies. H3O plus concentration, this is just the formula for percent ionization. But H3O plus concentration is not dependent upon concentration of acid you start with. So you want the one with the smallest denominator, because the smallest denominator is going to give you the biggest percent. If you have a smaller denominator, you're going to get a bigger number. So in this case, the one with the smallest amount is going to give you the biggest. Hope that helped. Okay, I kind of blacked out there for a second. Gave you the wrong information or the wrong formula. So, but actually, the right formula has a better, easier to understand explanation. Okay. So the greater K in general? No, not the K, the concentration of your acid. So yeah, greater K will give you a greater percent ionization, but in this case, the K is the same for all of them. It's all HF. It's only HF. You're only looking at HF. What you're looking at is which concentration of HF will give you the greatest percent ionization. So if you think about your formula, whichever one it will give you has the smallest denominator is going to give you the biggest percent ionization. So the smaller concentration is going to give you a bigger percent concentration, a bigger percent ionization. Yeah. Because your H3O plus is dependent upon your Ka value. It in itself is not going to change based on so concentration of the acid doesn't affect the H3O plus concentration. Only the Ka does. And because the Ka is a constant in this case, your H3O plus is not going to change. The only thing that's changing is your concentrations. So that's why it's not going to change. Okay. So given the following equilibrium reactions, which of the following will cause the reaction to proceed to the left towards reactant? Okay, so if I decrease A, it's going to proceed to the reactant. Because if I decrease this, it's going to want to shift back to increase that, because now you don't have enough reactant. If decrease the concentration in D, it's going to shift away. So it's going to want to increase. So it's going to decrease the concentration of reactants. So it's going to shift towards the products. So no, not 2. 3, increasing the pressure. If you look at the moles, you have 6 moles on the product side. So 6 mole product and versus 5 mole reactant. So you have more product than reactant. So increasing your pressure shifts towards the smaller moles. So it's going to shift towards the reactant side. So that is a check. That looks confusing. This isn't, no. This is a yes. Increasing the temperature is exothermic. So increasing the temperature is going to shift away because you can treat temperature as if it is a product. So if you increase the product, it shifts back towards reactant. So this is a yes. Increase the concentration of C. If you increase the concentration of C, it's going to compensate by shifting the equilibrium back to reactants. So that is like introduction of a catalyst. No, never. It doesn't affect the equilibrium. Remember that. If you remember nothing else, remember catalyst does not affect the equilibrium. Please remember that. So your answer would be D. Okay, so let's see if I can separate these. Which of the following acids are listed in order of decreasing acid strength, or the following are listed in order of decreasing acid strength? Which of the following is the weakest base? Okay, so a strong acid has a weak conjugate base. So acid strength, base strength is the opposite of acid. So if you do this, you write all of their bases out. I think I would prefer. So 2 minus CH3 COO minus CLO minus and CN minus. This is just gonna flip. So instead of greater than, it's gonna flip to less than. They're all gonna flip. That's just how it works. Stronger, and the reason why is because it wanted to give away an H. Like a strong acid, stronger acids means that it wants to donate an H. So if the acid wants to donate an H, it's not going to want to go back to the acid because it wants to donate the H. So if it's a strong acid, it wants to dissociate. Whereas if it was a strong base, it would want to associate. So it's like the opposite. Strong base means weak conjugate acid. So stronger the base, the weaker the conjugate acid. Or in this case, stronger the acid, the weaker the conjugate base. So for the reaction, O2 plus 2F2 goes to 2OF2. The Kp is 0.41 at 550 Kelvin. What is the Kc at the same temperature? Okay. I swear I forgot the equation. Okay, so I remember. Kp equals Kc times RT, change in moles. Be aware of the phases. So you got all gases, so you're all good. So you got 2 moles of gas on the product side and 3 on the reactant side. Okay, so your Kp, or sorry, you know what Kp is. So 0.41 equals Kc times 0.0821, because this is the gas constant that you use, times 550, and it's going to be -1 to the -1 power. because you have less product than you have reactant, less moles of product. Okay, so work that out. And you're going to end up getting D if you work that out. Okay, so at 300 Kelvin, the KEQ is 2.2 times 10 to negative 5. What is the KEQ for the reverse direction? So you just flip it. So K forward is 1 over K reverse. K reverse is 1 over the K forward. So solving for K forward, it's just, or K reverse, just 1 over 2 times 10 to negative 5. So in an aqueous solution, you got methane would act as a Bronsted-Lowry base, but a Arrhenius. So a Bronsted-Lowry base is a proton acceptor. Oh, but not a Arrhenius base. So it's a proton acceptor. So pretty much, it's not going to be an acid. And the reason why it's not going to be an acid is because of its structure. It looks like this. So you got H3. Let me do this differently. You got that H here and H there. You got this lone pair. And it's mostly because of this lone pair that it can donate these electrons. But it's not necessarily going to increase the OH minus concentration. That's the definition of Arrhenius base, is that it increases your OH minus concentration, but it's not necessarily going to do that. That makes sense. Or I guess I'm not necessarily. It's just if it's. I know it. Arrhenius acid increases H plus, but I'm not necessarily sure. Maybe Arrhenius base also just decreases H, but this H plus, no, not gonna decrease the H plus concentration. That makes sense. It's not a Lewis acid for sure. For sure, it's not. And you know it is Bronsted-Lowry base. Because it can donate these electrons. So if you want to work by process of elimination, you know for certain it is Bronsted-Lowry base because it's going to donate these electrons. It wants to, because it got a lone pair there, so it can donate them. It has electron density that it can give away to something else. Think about this is like similar to like NH3. So remember, NH3 is a conjugate acid or conjugate base of NH4. So it can donate that electron density to something positive or acidic. For a reaction of A plus B goes to C plus D, 6 ATM of A, 5 ATM of B are in the if there is 4 ATM of C at equilibrium, what is the Kp of the reaction? So this is one of the like slightly easier ice table reactions. So A plus B, and they're all, oh no, they're not all gases. So don't include D, because D is a solid. Sorry. I mean, you can. I usually put it there so somebody's not like, oh, where did that go? D, specify that as a solid. I, C, E. So you have 6 ATM, 5 ATM. So it's going to be minus X, 6 minus x, 5 minus x. And this is 0 plus x and 4. So you know x must equal 4. When I write I tend to write product side first. It doesn't matter if you write your x's properly. So if you do the minus x and the plus x in the right place, it shouldn't matter. But if you get confused, please like flip it. You would only hurt yourself in that case. If you know for sure, if you know where to put your x's, then it shouldn't affect your answer. If you're getting the right answers, that means you're putting your x's in the right spot. But usually if your x's are in the wrong spot, you're going to get something that doesn't make sense. Because how can you subtract something from nothing? You can't do that. So as long as there's a method to your madness, that's fine. So you know what x is. So your equilibrium concentration of A is going to be 2, and of B is going to be 1. Remember, C is still 4. So your KP is going to be 4 over 2 times 1, which is 2. That's your answer. Okay, so for chemical reaction, 4NO2 plus O2 goes to 2N2O5. Kp is 14.7. Which statement is correct if the initial partial pressures are that? So you just solve for Q. You just do so it's gonna be N2O5 squared over the NO2, 4, and O2, and then you're just plugging them in. So if you plug that in, you get 3.4 squared divided by 1.8 by 0.8 to the 4th. So you do that, you're gonna get a Kp value that is, so your Q is greater. I'm not Kp. Sorry, Q value. Your Kp doesn't change. Is 14.7. Okay, so your Q is greater than your K. So Q is greater than K. So you know that this is wrong, that's wrong, that's wrong. So if Q is greater than K, that means you have too much product. So if you have too much product, the reaction is going to proceed to the reactant. Because remember, this is the expression. So if this is big, so if Q is too high, that means your products are either too big or your products or your reactants too small. So products too big, reactants too small. Either way, you're going to need to So, what equilibrium expression? What is the equilibrium expression for the following reaction? Is a good trick for if you forget which way it goes. If that helps you, just be certain that Q's on the right side, if that makes sense. Well, technically, it's kind of pointing to the right. If you think about like an arrowhead is technically pointing to the right. So, I mean, if it helps you, you just have to make sure that Q is always first. Because if they switch it on you and they say K is K and they do K is greater than Q, then you'll completely mess up. So just remembering something like that, I think that's a struggle with me, like looking at it, having to be like, K, that's greater than. That's greater than. I just keep saying it in my head. That's greater than. Greater than. Okay, so it's greater than. And then like go on from there. Whatever it help, but make sure like if all these tricks that you use, a lot of the time, yeah, they really do write Q first. So just make sure that the situation is the same. That way the trick can the same that the situation is the same for when you first applied the trick and it worked. If it's not exactly the same, it's not gonna work. Okay. So what is the equilibrium expression for the following reaction? So remember, only gases and liquids matter. Only gases and aqueous matter. Yikes. It's a long, no solid, no liquid. So your equilibrium expression would, it's okay. It's gonna be your CO2. And remember the reason why, so these are all wrong. So the reason why A is wrong is because it doesn't take into effect that you have taken to thought or consideration that you have these sixes here that you need to put as your power. I feel like there's a better word for power that I've forgotten recently. So that's the end of that. If you guys have any questions, I would like to lastly go over the concept 3 study guide that I made. I posted it on D2L. So if you ever want to, when you're studying, like please like use this to help you. I'm gonna take a lot of load on your screen. Load it on here. Acids and bases, I personally wouldn't think about it too much. I feel like oftentimes if you think about it too much, you're gonna miss clues. Like they're usually big, like obvious clues that this is an acid, this is a base. You might be given the KB, like usually if you're given the KB, you're given the base. You're given a base. If you're given the Ka, you're given the acid. I don't know why it's not loading on your screen. It's on my screen. And also, if it helps, you can learn your strong acids and strong bases, but I don't think you're really going to get a lot of strong acids in this one. I think you're going to get more weak acids, but strong acids are the easy one. Like strong acids are going to completely dissociate, whereas weak acids, they're not going to, and that's where the majority of your calculations are going to come from. So this is just like, a concept list that I made. If you want to go through it as you study, this is just like to help you. This is like a guide to help you guys as you continue through your studying. I'm not entirely sure if you guys are required to memorize your strong acids and strong bases. It's always good to know. Like it could never hurt you to know the strong acids and strong bases. But if you're not required to know, oh yeah, she wants you to. Okay, so yeah, it's good to know your strong acids and bases. Like kind of, I mean, it depends on what major you are. But like I know I still remember like. Well, I probably remember more strong bases than strong acids because strong bases there's a system. Like it's usually going to be your alkali and alkali earth metals bonded to OH are strong bases. So like LiOH, NaOH, CaOH2, those are strong bases. The other ones like HCl, HBr, HI is strong acids. HF is not a strong acid. But yeah, and then the polyatomic, those strong acids like HNO3, HClO4, like you just gotta know those. Like there's no trick to it other than the strong bases. Strong bases are a trick. The first and second columns on the periodic table bonded to OH are usually gonna be strong. Other than H, don't include H. H bonded to OH is not strong acid or strong base. It's not. It's water. So yeah, just like those tricks, that's the only trick that you have. I mean, other than hydrogen bonded to halides, except for fluorine. Like fluorine doesn't count. Well, you have to know the definitions. So Lewis acid. Oh, I think I for the practice question, I think I messed up one of the definitions. Lewis base is a or electron donor. I think Bronsted-Lowry base is a proton acceptor. Sorry. So Lewis base electron donor. Bronsted-Lowry base electron or proton acceptor. So I guess that's why it's a proton acceptor, because it has that lone pair, so it can accept a proton. I usually still to this day get them mixed up. If that confuses you, you just gotta know those definitions. There's there's no easy way around it. You just gotta know them. It's the only way. I wish there was a trick. I guess the biggest trick is not really a trick. It's just knowing that every acid is a Lewis acid, every base is a Lewis base. So if it's a Arrhenius acid, like there's no such thing as something being Arrhenius acid and not a Lewis acid. Like it's got to be a Lewis acid if it's Arrhenius. If it's a Bronsted acid, it's got to be a Lewis acid. And then also that Arrhenius acids are Bronsted acids as well. So like the circles that she had, the concentric circle. So it's a circle inside of a circle. So Arrhenius is the smallest in the middle. Then Bronsted Arrhenius acids are Bronsted, so they get included, and Bronsted expanded the definition, and then Lewis acid or Lewis definition further expanded it even more to include even more things. So yeah, you just gotta look over them. There's kind of no easy trick for that, other than for knowing strong bases. But yeah, Bronsted, Lowry. If you're a chem major or a biochem major, it's gonna come back. So, but I think that's all I got for you. You can find this concept list in the SI folder in D2L. I think that's it. I'm gonna stop the recording.